Innovation and creativity are central to entrepreneurship. But what happens when you go beyond the edge? The Frontier Entrepreneurship Podcast brings you the world's first, the disruptive, the avant-garde. We take you to the frontier in conversation with the entrepreneurs who are the forerunners of the industries of the future. Get to know their world with co-hosts Braden, Kemp, and Tracy Morningstar. Morning sunlight catches a crystalline layer of ice formed on the surface of a perfect red apple, a beautiful but disastrous sight. Frosts cause more losses for farmers than any other climate-related hazard. But what if there was a way to protect farms and orchards with a biological approach? Today, we find out with Dr. Collin Juurakko, founder and CEO of Advanced Agriscience.
Hi, I'm Braden Kemp, here with my co-host Tracy Morningstar.
Hey, Braden.
Today in the show, we have Dr. Collin Juurakko from Advanced Agriscience. Dr. Juurakko, welcome to the show.
Hi, Braden and Tracy.
Collin, we met briefly before through bioenterprise Canada's Green Pursuit competition, where I recall you won a second place cash prize. I hosted that kind of scoring and judging session, and your solution really had the judges engaged and excited. I remember thinking the 3-minute pitch wasn't enough for me to learn as much as I wanted to about your technology. So I'm really excited to get the chance to talk to you today in a little more detail. And I want to start with a statement that your website makes: the world's first biopesticides for frost protection, directly inhibiting the cause of frost, which is a fascinating statement to me, because if I hadn't seen your pitch before, I would have assumed the cause of frost is cold and moisture. And I'd guess that most people without a science background would think the same. So to set some groundwork for our listeners, I think maybe we need to start there. What is the cause of frost on crops, and how can you stop it with a biopesticide?
Yeah, so you're right with the temperature. The low temperature has to be there for frost to actually form. But for it to actually form, it has to be nucleated. So those ice crystals have to form somehow. They have to be nucleated by something, whether that's a biotic nucleator, so a bacteria, or an abiotic nucleator, so that can be dust, soot, salts. But in our case, for agriculture, we're typically looking at those late spring frost events, when the temperature just dips down overnight. And in those situations, the most potent nucleator is actually ice nucleating bacteria. So it makes frost form at temperatures as warm as -2 degrees Celsius. So in the late spring, your crops are at a critical developmental stage. The temperature just dips down to, -2 overnight. And now you can have all this frost forming at a very high sub-zero temperature. And that is caused by ice nucleating bacteria. So we can directly inhibit that bacteria, disarm them of their capabilities to actually nucleate that ice. And if ice is able to nucleate, we can also arrest that molecular ice crystal growth and try and prevent the damage to actual plant cells and tissue.
That's incredible. Maybe we can spend a minute on the term biopesticide, or sometimes you also hear biologics. It isn't a brand new concept, but it's certainly something most people outside the industry aren't used to hearing. Can you give us a bit of background on the term biopesticide?
Yeah, so biopesticide is kind of the regulatory world term. You can also, call them biological inputs, biologicals, microbials. There's a lot of interchangeability, but when it comes down to the semantics and the regulatory world, biopesticides, biofertilizers are the terms they like to use. And that's sort of kind of where we are right now as well. Is frost a pest? Are we a biopesticide? That seems to be that's the way we're going. So biopesticide really just refers to a biological, a bacteria that is used in agriculture to inhibit a pest. And then in our case, that quote unquote pest is frost.
Awesome. Very cool.
I'm also going to once again quote something that you had said: treating the symptoms and not the cause of the frost. Can you explain how the technology targets the cause of frost damage in crops rather than just managing the symptoms?
Right. So today, most growers, they try to warm the plants with the existing technologies. So looking at that, we see irrigation. A lot of growers will treat their crops with irrigation in the frost conditions. The water freezes, releases heat during that phase shift to ice and warms the cells and tissue that way. Or you can have these big frost fans that circulate the cold air and try and warm the plants that way. They have heaters that burn fuels to try and warm the plants, or a lot of places in the world as well, they'll just straight up burn candles within their crops or light fires and try to warm the plants that way. So most of all these methods, they're really just trying to treat the symptoms, warming the plants, as opposed to treating the cause of the ice nucleation itself. So if you can imagine you're burning fires in the crop, all that heat is pretty much just going straight up. It's very inefficient, very unsustainable, and it's also expensive. You have to buy the materials, have labor out there to light the fires, maintain them, reignite them, all just to warm the plants. Versus what our approach is doing is straight targeting the cause and trying to prevent the ice from actually nucleating. And if it is able to nucleate, prevent direct cellular damage within the tissue.
Collin, I toured recently one of the largest apple producers in Ontario. I think one of the largest apple producers in the country. And they were talking about several frost events that happened. And they mentioned managing it with some of those technologies that you just mentioned there, heaters and giant fans. But they had helicopters come in, I guess, to move the air around. And it struck me that seems to be an expensive endeavor and not all that great for the environment.
Yeah, exactly. It's the same principle as using the fans, just trying to recirculate that cold air and get it off the plants. But those, you need a helicopter nearby. You have to reserve it ahead of time, and it's always just burning fuels, and it's loud too for your neighbors.
Yeah, the neighbors don't like that.
Yeah. So our technology, what we're hoping is that we can, eliminate all those emissions, eliminate all those needs to have to, reserve a helicopter, install these expensive fans. Maybe a lot of smallholder growers just can't afford those expenditures. And so what our technology is trying to do is eliminate those emissions, reduce the barriers to frost protection, increase equitable access to climate resilience.
The treatment itself can be a seed coating or a spray. Is that correct?
Yeah, so that's what we're trying to develop it into. So a seed coating application would be, the broad acres, your wheat, your canola, where you have such large amounts of cropland, but it's just traditionally been totally uneconomical to actually implement frost protection. So in that case, these technologies can be incorporated as a seed treatment, and a grower can, just seed normally with no extra effort on their end, and, maybe seed even a week earlier now because they could have some sort of frost protection. And if we get that late spring frost on some spring wheat, then the grower would typically, they just eat the losses and reseed if they need to, versus if we can prevent those losses and maintain yields, maintain productivity for no real extra effort on their ends. And, in the terms of the high value crops, your vineyards, your tree fruits, your tree nuts, your veggies, these cases would be a shelf-stable, wettable powder that a grower can mix with water and spray on the crops, just like they do any other existing pesticide or chemical. And that case would the bacteria, the biopesticide, would land on the plant, set up shop, and prevent those ice nucleation events and ice damage. And in these cases too, it's a shelf-stable powder, so a grower can purchase it, use it as needed, just keep it over multiple seasons, so it's not like a one and done. They can buy it and use as is needed. So that's what we're trying to do: a sustainable, equitable, low cost solution that they can use as needed and not have to recurrently buy and not be able to use.
If they seed it at the beginning of the year and it's 5 to 6 months down the road, do they have to reseed?
Yeah, so those are some questions we need to answer in our field trials. We need to see how long does it last, once it's applied. The literature suggests, these types of products, they last around 2 weeks, and then they just sort of die off. They're biologicals, which is one of their big benefits over conventional pesticides. There's no runoff to deal with. There's no additional chemicals. They're also very specific. They target the one thing they're meant to target versus broad spectrum traditional pesticides. But in terms of, the seed coatings for a broadacre crop, the idea is that we can, allow a grower to seed maybe a week or two earlier, or just survive those early frost events that would happen when right after they seed. And then in the high value crops where it's a spray application, we would see an application maybe a few days before a forecasted frost condition, and then the products would set up shop and prevent damage during those few days of frost conditions. But these are just things we don't know yet. That's what we need to find out and answer in the field trials in the real world settings, so we can provide real world data to show growers. But that's what we're focused on now.
We talk about that, the pilots or the field trials a little bit. What does that process look like, and what are the timelines?
We have to get our permission from the regulatory body. So in Canada, that's the PMRA. In the US, that'll be the EPA. So that's filling out all the paperwork for the government, waiting on their timelines to hear back, getting those approvals, and also bringing on partners who can trial the products as well, and actually producing it, sending it to them, and just getting the trials in place and done. And then not hoping, that we actually have a frost event that we can get real data from.
In some ways, especially in Canada, the regulations around agricultural technology can be tricky to manage.
Very difficult. It's so for the PMRA, we have to submit the notification 6 months ahead of time. For the EPA, it's 3 months ahead of time. The biggest hurdles really are just government timelines and government fees. We have to pay the fees and hope they can actually meet their timelines that they say. We do have Dr. Deborah Henderson. She's the director at the Institute for Sustainable Horticulture here at KPU Langley, and she is just a breadth of knowledge for the regulatory landscape, and she's really helping me out with that front, and I'm very grateful.
Yeah, going into that, can you tell us a little about the inspiration behind the development of these frost-protecting biopesticides for agricultural frost protection, particularly how Virginia Walker's work at Queen's University and Steve Lindau's UC Berkeley that shaped the creation of this particular innovative technology?
So all I've ever wanted to do since I was a kid was build a company, that can have real world impact and make a difference. And I went out to Queens to do my undergrad, took a course with Virginia, loved it. And I just cold emailed her, asked her if she had any, research opportunities in her lab. Sure enough, she had one, agreed to take me on because I had a lot of medical issues when I was in first year and my GPA was not the best. So I didn't get a position in, doing your traditional undergrad thesis project. But Virginia took me on. She took her chance on me. And, I guess I made a good enough impression, worked hard enough that she took me on as a master's student. That led to a PhD. And we kept answering questions and asking more questions and doing some really good research. And by the end of it, we had this technology that we could commercialize that, I thought we could use to actually make a difference, and pretty much moved home and started figuring out how to do it and get it up there. The actual topic of frost protection, though, freezing tolerance, was one of Virginia's research questions that she'd been working on for some time. Her lab was focused on the genetics of stress tolerance. So she was working in a number of systems, plants, fisheries, and zero gravity, actually, on genetics. So she's a very broad, very good researcher. And I entered her lab, and she kept me on, took a chance on me when no one else would. And that just sort of led to where we are today. So I'm also very grateful to Virginia. And the work done by Stephen Lindau at UC Berkeley back in the 80s, they sort of were doing what we are trying to do way back then. And they were targeting ice nucleating bacteria through competitive exclusion. So instead of actually inhibiting the nucleation itself and inhibiting ice crystals, they were trying to inhibit the bacteria through competitive exclusion, just trying to outgrow it per se in the biological system of plants and trying to prevent frost that way. But back in the 80s, this was sort of when, genetics and synthetic biology was really emerging, and there was a lot of questions, a lot of unknowns, and a lot of pushback on this technology, and they just got drowned out in regulatory fees by the government and activists destroying the the field trials plots. So it just seemed like it wasn't the time for that technology, and it just didn't come to fruition. But very pioneering work by Dr. Linda at Berkeley, and we're hoping to stand on the shoulders of giants and try again and see if we can make it work this time.
It sounds like perhaps some social concern around the technology at that time. Is that still a potential hurdle for you, or is that mostly past now?
Yeah, there's actually a really great article in Time magazine from the 80s called Science Fighting the Biotech Wars from Monday, April 21st, 1986 by Leon Jaroff, Jaroff. It's a great read. It's not too long, but it describes just the absolute pushback and the activism by certain groups that really just did not want to see this. The technology was brilliant. It could have, if we had it in place by the 80s, we could have had so much more progress, but didn't happen. But I think today there's a lot more education. There's a lot more work. The regulatory world is very streamlined. The fees are all streamlined. So they can't just drown you out in more and more and more fees. So that those issues seem to be okay now. But the public perception of genetic modifications might need a lot of we'll need a lot of transparency on our end and just full transparency and open access to all the data, all what we're doing. And I think with all new technologies, there's always pushback. Like, seatbelts first came out, no one wanted to wear a seatbelt. But with this technology, what we're hoping is that we can show just how much good it can do for the world and how the benefits can really have an impact. And we're hoping that, like seatbelts, they become a no-brainer for agriculture moving forward. We need to produce 50% more food by 2050, and we need to do it sustainably to continue population growth and success. So that's what we're hoping, that it is accepted and we can make it work, and in the eyes of everybody, that we can show just how much good it can do.
We live in an area that obviously deals with frost, but what is the scope of croplands that could have trouble with frost from a global perspective?
64% of all arable land experiences sub-zero temperatures.
Wow.
That is a quote or stat that I memorized from grad school. But yeah, so it is a big issue everywhere, and it's a growing concern. It's increasing in frequency, severity. Climate change is, we see extreme weather everywhere. So really a frost could hit anywhere. Maybe not so much the tropics and the equatorial regions, but that also depends on the elevation. We see frost events in Kenya on their tea crops. We see frost events in California. We see frost events happening everywhere. And the issue is that, you get a frost event at the wrong time, a single degree or a single hour, at a critical crop development stage can wipe out the entire crop. So it's a big issue all over the world, and we see it, where you wouldn't necessarily expect it.
You mentioned being inspired and influenced by individuals such as your parents and your graduate supervisor. How have these personal influences shaped your vision for the future?
My parents always, instilled in me work ethics and, fairness, doing the right thing. So my parents really inspired me just to work hard, follow, what my visions are, and my visions are, bringing this technology, in an ethical and good governance way to the world. My graduate supervisors, doing good science that can be repeated. Another one, Jensen Huang, when he started NVIDIA, he had no idea what he was doing, building a company. So that's sort of another inspiration, figuring it out, as a scientist, as an engineer, being able to create a company. With science, keeping the science in mind, keeping the vision in mind, being able to deliver good products that are accessible. Just other great scientists who do good science, and with translating that science into real world impact. Those are a lot of my inspirations. But first and foremost, my parents.
How did you move from biologicals to an entrepreneur? You want to bring this product to fruition, but you need to be an entrepreneur.
Yeah, it's all there wanted to do. So after grad school, I just started figuring out how to do it, learning the world of business, reading, good mentors, good advisors, just talking to people, learning how to do it, going through different programs. I went to a program called Entrepreneur First in Toronto, started learning a bit there. Did another program called Thrive Academy. That one was focused on agriculture, so we learned a lot more there. It's just a matter of learning, and bioenterprise as well with Braden. Learned a lot there with that program and with the mentor Mike Mannion. So just figuring it out, finding a way, making a way if you can't find one, and just learning how to do it all.
Collin, it sounds like you're an entrepreneur scientist and not a scientist entrepreneur. And that doesn't seem to be too different. But I've spent a lot of time working with startups and entrepreneurs and small businesses, and the space you're in where someone or a team of people is taking really good research and trying to find a commercial home for it often is a really tricky path, because you end up with really smart scientists that do really good research but struggle to get it out of the lab and into the world of business. So I think it takes a bit of a different way of thinking, like you're describing, to commercialize these these really science heavy businesses.
Yeah, it's a totally different way of communicating and thinking about it. In science, you write these papers that no one's ever going to read, with all the scientific academic jargon that, reading my own papers, I'm thinking, what the heck does this mean? I have to read it 5 more times before I understand my own writing from a couple of years ago. But it's an entirely different way of communicating. You have to communicate succinctly, effectively. That's just on just being able to communicate. You also have to think differently in terms of being able to actually commercialize, develop, scale up something from the bench top to a way that it can be used in the world. So it's a whole bunch of different aspects, different ways of writing, different ways of thinking, and just trying to do it all at once,
and ultimately bringing it to the customer.
Yes.
I was with a group of farmers 2 weeks ago talking about it, specifically about adopting ag tech on the farm, and the consistent message from all of them was that it has to save them time and money, which is interesting, because normally you hear, oh, you can sell a solution that saves time, or you can sell a solution that saves money, and it sounds like, albeit sample size small, in the ag world, it's both. And it seems like your product could be one of those that can do both. Have you had any feedback from farmers yet, at least conceptually?
Yeah, so it's always the same thing that I hear too. You have to save time and money. It can't just be a marginal improvement, a little bit better. It has to be night and day. It has to be time and money saved, and it has to be effective. And that's what we need to show in our field trials, that that it does work, that implementation will save time and money with real world data, on a broad variety of crops, so we can show each grower their specific use case. And that's what we're trying to do, save time and money for growers.
Any specific crops that you're working on first?
Yeah, our first crops we want to hit are the high value ones: vineyards, tree fruits, apples, citrus, ginseng as well. There's a lot of high value crops that are really affected by frost, but the beauty of this product is that it could be crop agnostic. It can be applied on a broad variety of crop types, and that's what we're trying to do: bring it to every crop type. But we have to line up and hit our first targets first, and be able to show real data for each crop type.
Just a side note, talking specifically about the crops, but I was just wondering about the soil. Is there any data on how it affects the soil?
Yeah, so the bacteria, we actually found it in Canadian soils. It's a soil bacteria that can colonize plants and live within them, and it's a beneficial bacteria. So when we look at frost, the main issues are in the buds, in the shoots of the plant, the above soil portions. We did some work looking at the freezing or low temperature stress in plants, and in the above portions as well as the soil. And what we saw in our our simulated controlled lab frost events, that the soil really didn't have much changes in our quick short frost events. So that's why we're just focusing on the above the ground part where the main damage occurs in these unexpected late spring frosts. But we don't have much data from the soil under simulated frost events.
You mentioned that the bacteria you found it in Canadian soil. Does that help you from a regulatory perspective?
Yeah, so a lot of for the PMRA, for example, they want to see that it's a regionally local bacteria, and that does help in the regulatory world.
When you say regionally local, this product has applications worldwide. Are you going to find this bacteria as regionally local, wherever you go, or are you going to be looking for regionally local bacteria that you can work with in other geographies as well?
So the genus, the group of bacteria, it's ubiquitous. It's pretty much everywhere. But the specific strain that we found is the one in question that we want to be able to use, and that's what we found in the Canadian soils. We found it in Sydenham near Kingston, from Virginia's farm actually. And another group, the reason we found it was because a group in the UK also found it, and they had sequenced the DNA and published it to open databases, and that's how we found it. So these are the two circumstances of it being found, a specific strain in both Canada and the UK. So maybe it's not crazy to think that we'll find it elsewhere, and that would help regulatorily. But there are similar ones that just don't have the exact same capabilities, but undoubtedly they're everywhere in the world in the soils.
Interesting.
I just had one question related to your funding. You mentioned non-dilutive funding for your project. Could you just elaborate on the significance of this funding model for your business strategy?
Yeah, so typically, a pre-seed company will try and raise VC capital, and they'll take 40% of the company. They'll own a giant portion of the company, and then they'll try and maybe they won't try. It's not crazy to think that they'll fire a US CEO in a few years and put their own person in who serves their interests primarily. But that's what I'm trying to avoid. I'm trying to keep our technology low cost. I don't want to be able to or take on a big VC that will control the company and then force me to maximize the cost. So then not all growers can access the technology. So I'm trying to bring on non-dilutive funding, grants, fellowships to get this research done, get it done, and maintain the company vision of what we're trying to do. And that's another reason why we're actually a public benefit company. We're a B Corp. So in our articles of incorporation, we're mandated to deliver value directly to growers to help them with climate resilience and frost protection. So that's sort of the vision, being able to maintain the vision of the company and control at this stage, and get non-dilutive funding to really develop the science and de-risk it a lot more, get our field trials done, and then bring on a strategic investor later on that shares the vision and do that at a much higher valuation.
Collin, are you finding that the environment, I guess mostly the government funding environment, are the supports there to find that non-dilutive funding to keep you going?
Not particularly in Canada. A lot of the grants are, they'll require cost sharing, and at the stage, we at such an early stage, we don't have much money to share, and all the grants in Canada, they're like, you need to be in operation already for 2 years, you need 5 full-time employees, you need 100,000 in revenue already just to even apply. Or you have to be a faculty at a university, you have to be a professor to get some research grants. But even if they don't have those requirements, it'll be a 50-50 cost sharing, and then maybe it'll have a minimum budget of $100,000. So then you have to bring $50,000 to the table. But at an early stage, you don't have that 50,000, and then you look to the States and they have all these a Sabre grant, $400,000 USD. You can no cost sharing. They have all these grants with no cost sharing, no barriers to entry. So it's a lot more difficult to do in Canada, but it's home, and I don't want to make it work here.
Yeah, it's something that I've heard before, and not just in ag, but particularly in ag, that funding environment is tricky right now.
Very tricky and very slow, very difficult, a lot of barriers, especially as a brand new startup.
Does this technology have applications outside of agriculture? Where else could you go with it?
Yeah, so if you boil it down to this core of the technology, we're protecting a cell from breeding damage. So there's a number of applications that eventually the next maybe 10 years we want to start looking at organ transplants. cryopreserving whole solid organs, complex tissue, eliminate the geographical and temporal constraints for transplants. So, maybe someone on the other side of the world has a match. Now you can get that organ across the world, or you can store it until you do find a match. So save lives, reduce public healthcare costs, and improve patient outcomes. So that's a big application of the technology that I want to look at in the future. Food preservation as well. So, freezing, storing food, maintaining that quality and over time, so you don't get ice crystal damage. Breyers tried doing something in the late 90s, early 2000s with similar technology to prevent ice growth in their ice cream. But turned out the average consumer does not care enough or want to pay, that much more to, marginally improve the quality of ice cream. But boiling it down, there's a number of applications that this technology could be applied to. And that's just the frost damage aspect. There's in my vision is a whole entire library of climate resilient biologicals for agriculture, low cost, easily accessible technologies that can be used on demand for resilience without even touching the host plant genome. So being able to do it faster regulatorily and a lot more cost efficiently, as opposed to developing whole new varieties of crops that maybe not everyone can afford or get access to.
I think that's a great spot to end. It kind of summarizes what you're working on right now, but also some really fascinating things you might get after in the future. Dr. Juurakko, thanks so much for joining us today. It was great to catch up and learn more about advanced agriscience.
Thank you, Braden and Tracy. It was great to meet you.
We'll be right back after this short break.
Bioenterprise is Canada's engine for food and agricultural technologies, a vibrant community dedicated to driving industrial innovation. Learn more at bioenterprise.ca.
We return to the Frontier Entrepreneurship Podcast with co-hosts Braden Kemp and Tracy Morningstar.
Tracy, I really liked Collin's commitment to bringing this technology to the world in what sounds like a responsible and ethical way. I know the company still has a lot of hurdles to cross to commercialize, but it's a really fascinating bit of science. And I think it can be a big cost saver for farmers and potentially improve the stability of the global food supply.
Absolutely. And I really appreciated where his inspiration came from Virginia Walker at Queen's University and Steve Lindau from UC Berkeley. Now he's bringing it forward once again, and hopefully, he could see some real success.
Yep. I think the world is probably a little bit more ready for this sort of biologic frost or crop protection in general than it would have been in the 80s.
Protecting the science is what he said. And I believe that he is determined to do so. He's an entrepreneur, he's a scientist, biologist, and he's able to work both worlds.
I want to thank Dr. Collin Juurakko again for joining us today. And always, Tracy, thank you. This was a really interesting conversation.
Yes, absolutely, Braden.
We'll see you next time on the Frontier Entrepreneurship Podcast.
Next time on the Frontier Entrepreneurship Podcast, we speak with Ben Fagan, CEO of Agritech North, a social enterprise and B Corp tackling food insecurity in remote communities. This edition of the Frontier Entrepreneurship Podcast was made possible with the support of FedDev Ontario and the Government of Canada. The executive producer is Robert Washburn. I'm John Hayden. To find out more, head to our website, nventure.ca. Thanks for listening.